folks, this is the solutions video for the trig optimization handout. I'm going to go through all of these questions and kind of talk through the solutions that are already posted. So question number 1 says Terry has a piece of board that's 10 meters long. That's a very long piece of board. I think this was probably changed from feet to meters. So he wants to go around a hallway that's 4 meters wide and make a 90-degree turn into a 3-meter wide hallway. So he's walking down this hallway, and yeah, now I'm pretty sure that these were changed from feet to meters to be more Canadian, but make less sense here. So he is carrying this board, and it's going from one hallway into another hallway. And we want to know, and you guys have maybe done this if you've ever helped your family move some furniture or trying to angle things around a corner, can it actually fit? Now, with this question, we're going to say that this board, the width of the board, we're just going to assume it's negligible and not include that in our calculations, because that would make this a lot harder. But I'm just going to say that the board is just one piece like that, and we're not going to worry about it actually having kind of a dimension there. We'll just assume that it's pretty narrow and not going to matter. So we want to know, can this board fit around the corner? So we want to know the longest length here that can make that turn. And to do that, I'm going to divide this up into kind of two pieces. I'm going to look at how much of the board is in that second hallway and how much is in the first hallway. And then the length of that board, we'd have some function that the length, I could use L, but that sometimes looks like a 1, is x plus y. Maybe I'll just write length equals. That's what I want to find the maximum. Find the longest board that can fit around that corner. Now, because this is in the trig section, we know that it's going to change these x and y, like how much of the board is in each hallway is going to change based on the angle that you're moving it. So we know that there's some kind of angle relationship when the board is let's say back here and kind of going like that. This would be a different angle there, and as it moves around, it's the angle from the board to the wall that's really changing here. So I'm going to try and express x and y in terms of that angle theta. And I'll erase this yellow one because I don't really want to show multiple spots of that. So I've got my x and my 4 meters there. So I know that I can make a triangle here, and that this would be 4, and from this triangle, that's going to be 90, that's theta, that's 4, and that's x. So sine theta is going to be 4 over x, and x is equal to 4 over sine theta. Kind of similarly, I would have another triangle. If I make this triangle here, hopefully you guys can see that this is like an F pattern with these two parallel lines and this transversal, that this angle would also be theta. So if I look at this triangle here, I'd have 3 theta and y. And then that would tell me that cos theta is equal to 3 over y, or y equals 3 over cos theta. So that's going to be my expression for x and y in terms of theta. So I'm going to have a length function in terms of theta. So maybe I'll say L at theta equals 4, and I'm going to write sine theta to the exponent -1 to make my derivatives easier, plus 3 cos theta to the -1. Now, when I take the derivative here, I'm going to get -4 sine theta to the -2 times the derivative of sine, which is cos theta. Then I'll have -3 cos theta to the -2 times the derivative of cos theta, which is negative sine theta, using the chain rule there. Cleaning this up a little bit, and I'm going to want to say that L private theta equals 0. So I'm going to take this term, move it to the other side, and I'm going to put that sine to the -2 on the bottom. So I'm kind of making it equal to 0 just to save space. I'll have positive 4, bringing it over to the left, cos theta on top, and then a sine squared theta on the bottom. It's not a very neat exponent there. So again, I'm just bringing this whole term over to the left because I'm making it equal to 0. I'd have a positive 4 then because I bring it over, cos still on the top, and I'm putting that sine theta to the -2 on the bottom. On the right-hand side, I've got a -3 and a negative sign, so that's going to end up being positive 3 sine theta over cos squared theta. Then if I cross multiply, I get 4 cos cubed theta equals 3 sine cubed theta. Remember that if you have sine and cos both in the same equation and you're trying to solve, almost always you're going to want to divide both sides by cos or divide all terms by cos to get a tan and get kind of rid of the sine and cos together. So I'm going to divide both sides by cos cubed. There, they'll cancel. I'm actually going to also divide out a 3 on both sides just because I kind of see this coming. And that will cancel as well. So then I'm going to get 4 over 3 equals tan cubed theta. So tan theta is the cubed root of 4 over 3. So that's what I have to solve to figure out whether this board will fit around the corner. So I'm going to just add a screen and know that I ended up at a point where I had tan theta is the cubed root of 4 over 3. And let's put some restrictions here on our theta. Kind of going back to that original picture. This is going to have like real life situation here. If you're measuring this theta as how it's going around the corner, the smallest theta could be is if you put the board like exactly parallel to that wall, right? If it was exactly kind of parallel to the walls in this first hallway, theta would be 0. And eventually you're going to like curve the board around, and then you're going to have it exactly parallel to the second hallway, and then theta is going to be pi over 2 or 90 degrees. You're not going to have, you're not going to ever have like the board flipped around to the other side. You're never going to have like a bigger than 90 degree angle. So I think that we're very well within our rights to see that theta is between 0 and pi over 2. So we do have nice endpoints to check. That's only in the first quadrant. So if I do, again, making sure your calculator is in radian mode and solving for your angle here, if we do tan inverse of the cubed root of 4 over 3, figure out what that is, keep a bunch of decimal places just in case, and I get 0.83327. That's probably more decimal places than we need, but it can't hurt. So we would want to figure out, we're going to check what would be the length at each of these sections. So the length, and we may actually run into a little bit of trouble here because if we are putting in like a 0 or a pi over 2, we're going to get like 4 over 0 or 3 over 0 for these. Because if you had the board like parallel to the thing, you're actually going to be able to fit an infinitely long board. So you could maybe just test a very, very small angle. It is a little bit trickier to kind of do the sine analysis here, but we would want to kind of check the length at a very small angle, just quite close to 0, and the length at a very big angle, like pi over 2 minus 0.001. These are going to be very big, because if you're not at, and you can put those in your calculator, whatever, very small or big. If you're at a very big, almost 90-degree angle, you can fit a super long board here. And if you're at theta being like a very small angle, like you can fit a very, very, very long board. We're not interested in that. We want to know what the shortest distance is that will still fit, because this is going to be what's the minimum board length here, and we want to know, is that shorter, like that minimum length, is that shorter than the length of our board? So if we check this critical number of 0.833, the length at 0.83327 is about 9.87 meters. So this is the minimum distance that you're going to have as you curve around. Of course, the board can fit if it's almost all in the first hallway, but it will have to fit within that range. So we could say, therefore, no, it will not fit. He has to cut off, it would be 0.13 meters or 13 centimeters. So you'd have to cut off a little bit. It's not quite long enough to fit. Or it's a bit too long, pardon me, to fit. Okay, question number 2. This one is, I think, a little bit easier for most people because we are given the function here, and we want to find the maximum and minimum displacement. So we know, if you're thinking about like particle movement, if this is moving horizontally, the maximum and minimum displacement back and forth, that's going to be at the max min points, and that's where the velocity is 0. If you're going this way and then you stop for a second, turn around, not a second. You stop instantaneously, you have a positive velocity, negative velocity, positive, negative. For a split second, right at that maximum distance away, you're going to have a velocity of 0. So that's what we're going to be looking for. So here we've got 2 sine t minus cos t, and we are given an interval. So we want to find the derivative of my displacement. So this would be 2 cos t minus negative sine t. So that's going to be plus. And we want to find where this derivative equals 0. So that would be negative sine t equals 2 cos t. And again, sine and cos, you might think, oh, I can't solve this because I don't know where those are equal. Whenever you have sine and cos, divide out a cos, and then you've got tan. So there we've got negative tan t equals 2 or tan t equals negative 2. So we want to find where tan is equal to negative 2. And t is, let's go tan negative 1 of negative 2. And again, making sure you have your calculator in radian mode. So negative 1.07 is what I'm given there. But we have to kind of figure out, that would be my related acute angle. Well, it's actually not related acute angle. If I think about the cast rule, and where is that? So I know that I have tan and it's negative. So that's going to be in this quadrant. Yeah, it kind of is my related acute angle, but it's negative. So it will be down here in the C quadrant and in the S quadrant. That's where tan would be negative. So they're giving me this on my calculator, negative 1.07. I want to get that in terms of between 0 and 2 pi. So I'd say negative 1.07 plus 2 pi, which would be kind of like looping it around to there. And that ends up being 5.18. And then in the other quadrant, let's figure out what this one would be. Here you'll have pi minus 1.07, which ends up being 2.03. Oh, and I made a little error there with my copying that down, but I did have the numbers written out right. It's 1.107 there. So I've got my two angles. I'm going to test the endpoints and the critical numbers. So I'm going to find S at 0, S at 2.03, S at 5.18, and S at 2 pi. And we're just going to figure out what the maximum and minimum displacement is from there. So S at 0 and S at 2 pi are both the same. They're negative 1. S at 2.03 is 2.236, and this one is negative 2.236. So that would be the max and min displacement. So therefore the max in the positive direction is 2.236 at t equals 2.03. And we'd have a min of negative 2.236 at t equals 5.18. Here we go. This one is looking at kind of a 3D picture. So we are going to take a piece of sheet metal 60 centimeters wide, and this is sort of similar to one that was done in another example, but there we had we were trying to figure out how much to fold up on each side. Here we're looking for the actual angle. So I know I want to maximize the area of this trapezoid. So I have a piece of metal, whoops, wrong pen, a piece of metal 60 centimeters wide, and I want to basically maximize the area of the trapezoid if each of those are 20 centimeters. So I'm going to try and figure out what is my angle, and I'm going to put a theta in there. I know I'm not going to get the best results for big area if I fold them in, right? I'm definitely going to probably want to fold them out. And if I think, well, what's a real life restriction here? I think I can pretty confidently say that if I folded these 20 and 20 sides up into the center and made it like an equilateral triangle, that's going to be a bad for area, because for sure I could get a pretty good area just making it a square. This square here, totally bigger than that triangle. I can say that with confidence. So I'm going to start theta at 0, and you definitely wouldn't want to fold it past like a 90-degree angle here, right? I mean, even flat is a little bit silly, but I think that we can confidently say that theta is somewhere between 0 and pi over 2. So kind of between a 0 and 90. You're going to fold it from flat up to somewhere not past 90, because then it's going to start to get smaller for sure. So we want to figure out what the area, and this is a plus b for the bottom plus the top times the h divided by 2. So in a trapezoid, maybe I'll kind of draw this out here, where those all are. So that's A, that's B, and that's H. And that's what we want to figure out, what each of those are in terms of these 20 centimeter sides and our angle theta. So first of all, the A is easy, right? A is just 20. We know that that's true. H, probably not too hard either, because I have 20 there and an H. So I think I can pretty safely say, okay, H is going to be H over 20 is cos of that theta. So H over 20 is cos theta, so H is 20 cos theta. All right, so I've got my H, I've got my A. The B is a little bit trickier. And maybe I could put like a little X in there. And I might say B equals A plus 2X. Hopefully we're all okay with that. The A from the base is the same there, plus X and X on each side. So we would know that X, where can I squeeze this in? X over 20 is sine theta. So X is 20 sine theta. And we know that the A is 20. So I'm going to take that A is 20 and X is 20 sine theta and sub them in and get a good expression for B. So B is 20 plus 2 times 20 sine theta. And B is 20 plus 40 sine theta. So now I have what each of those are going to be. So here, I'm going to take my A and my B and my H and put them all into my area equation. So here I have 20 for my A plus 20 plus 40 sine theta for my B times my H, which is 20 cos theta, all over 2. So we definitely want to simplify this. We can clean this up quite a lot before we try to do anything here with the derivative. First of all, I'm going to take this 2, divide it into that 20, because that one's kind of a multiplied out. Because it's not plus or minus in here, you don't have to divide it in there. This is like just divided into one of the factors. So then I will have 10 cos theta times 40 plus 40 sine theta. Okay, I'm going to multiply that in. So 400 cos theta plus 400 cos theta sine theta. And I'm not sure if, you know what, maybe I won't multiply that in because I'm going to have product rule here. And I would have product rule in the previous one. I think I might just leave that. So now I'm going to find the derivative because that's where we want to find the minimum value or maximum, pardon me, value of water. So A prime is going to be the first 10 cos theta times the derivative of the second. So the derivative of 40 sine theta is 40 cos theta plus the second, so 40 plus 40 sine theta times the derivative of the first. So the derivative of the first there is going to be negative 10 sine theta. So I'm going to clean this up a little bit. So I'll have 400 cos squared theta minus 400 sine theta minus 400 sine squared theta. Now I really don't like this because I've got sine squared and sine and cos squared. So that's really kind of a lot of mess to deal with. I can't solve if I set that equal to 0. I can't solve if I have a sine squared. The sine squared and cos squared would be okay because I could divide out a cos squared and I would get tan, and that's fine. But if I divide that sine by cos squared, that's not tan. That's like tan over cos. It needs to be like the same exponent in all of them. But what I need to do here is going to be sub in the 1 minus sine squared identity for that cos squared. So here I've got A prime is 400 times 1 minus sine squared theta, because now I've got it all in terms of just sine and sine squared, minus 400 sine theta minus 400 sine squared theta. So I'm going to keep going here. I've got some really big numbers with all of these 400s, but I think that they're just going to cancel each other all out. I feel like I should just divide this whole thing by 400. So here I have 400 minus 400 sine squared theta minus 400 sine theta minus 400 sine squared theta. So if I divide everything by 400, I'm just going to slide this on to the next blank slide. And copy out from there. So here, I know that I want to find where the derivative equals 0. I really like to state that, make sure that you're being clear on what is happening. So I would have 0 equals, that's going to be negative 800 sine squared theta minus 400 sine theta plus 400, and dividing, 0 not a theta, divide out by, divide out by a negative 400 everywhere. So I'll get 2 sine squared theta plus sine theta minus 1. So I'm just dividing the whole thing by negative 400. Now I have a quadratic trig expression and I can factor that. So that'll be 2 sine theta there and sine theta. And I know I'm going to have a 1 and a 1. I just have to figure out which is negative and which is positive. I want to end up with a positive sign, plus sign in the middle. So that'll be plus and that'll be minus. So plus and minus. So I would have, this is where sine theta equals 1/2 or sine theta is negative 1. Now, thinking about your special triangles, remember that theta is only in between 0 and pi over 2. So theta, sine theta equaling -1 would be at 3 pi over 2. So that's inadmissible. And if I think about where theta equals 1/2, that would be pi over 6, or like a 30-degree angle. And the other case would be 5 pi over 6, but that's inadmissible. It's outside of the given interval between 0 and pi over 2. So I'm going to just check the area. So my area at 0, the area at pi over 2, and the area at pi over 6. So I'm going to take that, sub it into the area function, probably this simplified one, 10 cos theta times 40 plus 40 sine theta. And I know that if I had a pi over 2, that then that would be that cos would be a 0. So if you fold it out and it's just a flat sheet of paper, that's a terrible plan because the area is 0. If you take this and check area at 0, then that would be if you didn't fold it out at all, and you get 400. And if I take the pi over 6, then I will have 10 times cos pi over 6 and here I get an area of 519.62 centimeters squared. So this would be like an exact 90-degree angle. This one is if you have like don't fold it up at all, and like that's a terrible trough. And this one is if you fold it out at a pi over 6, fold it out by 30 degrees on each side. Now, I believe in the optimization handout, and I think maybe I misread this question just a bit. Determine the angle that you fold it by. I was picturing like how far we folded it up, how far we folded it out from there, but I think the actual angle is here and says pi over 3 in the answers, but they're looking at like what's the angle you folded it up by. So if you did it this way and got pi over 6, you are correct, but they were just actually looking for that outside angle, which would be the 60 degrees or pi over 3. Okay. This one I am going to, I think, just skip over because we did not cover this this year. That the type of derivative is a little bit beyond what we do. It's a really good challenging question for the setup, but you wouldn't be expected. There's a few too many things in there with the double angle of tan formula and taking a derivative that is a little bit trickier with a changing angle. Okay, the next one though, for sure, is a really good question. So what angle theta between two sides of a triangle with length 3 units will result in an isosceles triangle with the largest area, and what would that area be? So here we've got a triangle and we have that theta, and this is 3 centimeters or 3 units, it doesn't say centimeters, and that's 3, and we want to find a maximum area. Now, it is, I think the trick here is that a lot of people, we know, of course, we want to maximize area, which is base times height divided by 2, of course, for a triangle. And I think a lot of people initially think, okay, well, here's the base. I have to figure out that height and do all kinds of complicated things with like, well, what would this angle be? And how could I find this height? And how could I find this base? And there's a lot of things there that we just don't know. First of all, you're like splitting to make this height. You're getting like a theta over 2 on 1/2 of that. So then it's harder to have that in there. Then also, we don't really know much about the base, and I guess like you could maybe use cosine law, but that's super messy. I want you to shift your thinking that the base doesn't have to always be on the bottom. So if you're looking for area, we know a lot more stuff here. Why don't I just drop that down? And actually, I'm going to redraw this because I want to make it super clear that this is not an equilateral triangle. Like, we don't know that it's an equilateral triangle. So I'm going to draw that like super. Very isosceles. So if I were to drop a base down or a height down there, like at that 90-degree angle, then that would be my height. So I suppose I don't need to write it upside down. So that's going to be the height of the triangle. So I'm going to look at like this right-angled triangle here, and I know that sine theta is h over 3. And now this length here, that's the base, right? If I find this, if I find that as the height, and that's going to be a lot easier. So h is 3 sine theta, and the base is 3. So that's what I'm going to put in to maximize the area. So area is 3 times 3 sine theta over 2. So area is 9 over 2 sine theta. We do want to consider our restrictions here, like what would our limits on theta be? And I think that we are all probably okay with saying, well, this theta for sure has to be between 0 and pi. If it was 0, you would have an area of 0, and if it was pi, it would be like flattened out and not even really a isosceles triangle. But imagine if it was like almost pi, like that. It would be like those are kind of our limits of where this could be. So neither of these are looking like great isosceles triangles to maximize area. So I'm pretty sure the area is going to come at a maximum when we've got the derivative equaling 0. So here the derivative is 9 over 2 cos theta. And if I'm looking for where a prime equals 0, it would be where cos theta equals 0. And in that first, in that interval 0 to pi, that would mean theta is pi over 2. Okay, so we're going to check. A at 0 would have an area of 0. A at pi would have also an area of 0. A at pi over 2 would have an area of 9 over 2, or 4.5. So the max area of 4.5 units squared at theta equals pi over 2, or 90 degrees. So the biggest triangle is if this isosceles triangle has a right angle between the two equal sides. And that is it for trig optimization.